second edition of CodeUp in Bangalore. I'm Mansa, I'm your host for the evening. So, PayU, as you all know, is one of the leading payment service providers in India. We are across sectors like airlines, SMBs, and of course the startup community. So, we have CodeUp series as a part of our startup outreach program. We have another series called UpStart. So, that's for startup entrepreneurs. While CodeUp is for developers, where we bring domain experts to talk to you about various topics. So this topic for the day is cloud native app architecture. We have three great speakers with us today. Mohamed, he's the co-founder at B2B Networks. Vivek, he's a developer advocate with DigitalOcean. And our final speaker is Kalyansundaram. He's the lead Devops engineer at Media.net. So without further delay, I would like to call upon Imran to take the session.
Hi guys, my name is Imran. I handle the technology at B2B Networks. Since it's a small gathering, so that's okay. We have some set of people. I'm not audible?
No, it's live streaming.
Achha, it's actually live streaming. Hi guys, Imran here. I handle tech at B2B Networks. Okay, so let's get started with it. So I want to set in perspective the topic that we have. And the idea behind being cloud agnostic or cloud native in a sense is essentially to figure out how you can leverage the cloud strategy and essentially coming up to terms and up to speed with the multi-cloud strategy. Right? So one thing that you might have noticed in the last 1 year is that there are a lot of people who are talking about multi-cloud deployments where the underlying choice of deployments and technology is going to decide how efficient your multi-cloud strategy is going to be. Right? So, see, the minimum multi-cloud strategy that people have been following for so long is to set up a DR, let's say, and essentially to go ahead and set up like some redundant nodes in another availability zones. That is what people typically do. But a true multi-cloud deployment is something that which can run on across infrastructures of multiple providers. Let's say you have AWS, GCP, Azure, and so on, and in a seamless manner, be efficiently able to utilize what's the best in each of these infrastructure providers. Right. So with that, I set the scale for what are the challenges and how do you have an effective cloud native deployment. So one of the big challenges is that all startups and enterprises face is you need to be essentially cognizant of your technical debts in deciding an infra, right? So let's say one startup, one DevOps guy decided that hey, cloud A is my platform. So that is a choice that they have to live with for the next 5 years at least, until they get a larger team of people to rework that entire thing, right? So there's a certain amount of cost involved, there's a certain amount of technical debt involved in deciding which cloud do you want to use and so on. So you have to be very mindful of that, and obviously we are talking about the same challenges we had when we started out in the 90s, right? For example, people used to talk about interoperability between Microsoft, Linux, Mac, this, that. Now we are talking about in the same manner on the cloud. We are talking about like how do I migrate my workloads from cloud A to cloud B and so on, because there's no standardization. So once you are invested in a particular cloud, then pretty much you have to live with that choice for the foreseeable future that you have, unless you are taking a massive effort in restructuring that. So that is one challenge. And the vendor locking concerns are also there, primarily because of privacy concerns, primarily because of cost concerns, a lot of other concerns are there, to which there are like a lot of concerns in the community on what's your effective multi-cloud strategy. Now, I'm an open source guy, so my presentation is not without its slides. So the point that is being made out here is that for every native component of a cloud, you have a way to natively build that service on any particular cloud by using open source components, right? So the services that are there, for instance, your let's say your S3, Elasticsearch, and so on, they are very good for you to get started, right? So let's say you're doing a small POC and you want to get started. It's a very good way of having a jump start and getting to do what you're doing. But as soon as you hit the business end of stuff, all of this is going to come and cost you, right? Because this is like well abstracted from you. That's advantageous when you start out, but then when you want to really measure performance, when you want to really optimize your cost and so on, then you will have certain challenges. This is just one example, representative example of one cloud. Very similar examples you can take across other clouds as well, like GCP and your Azure as well. So let's talk about one important challenge whenever we talk about multi-cloud or cloud, right? Why do people move to the cloud? Is for the scale, right? Because no one wants to be able to manage all these tons of hardware in their local data centers. That era is gone. So what people are looking for is what do I scale, how do I scale, when do I scale, and it's also important that you understand what are all the challenges and you also understand what are the opportunities, because without that SWOT matrix, even though you might be on the cloud, you might still not be scalable. Right now, when suddenly like there's a traffic spurt, somebody comes and says, "Hey, can we just spend 5x extra and get things up and running?" You can't. Right? Case in point is the latest Kimbo app. Right? Didn't work because within 1 hour they had 3 lakh users signing up on that, and the service just crashed. Right? Because they were doing a POC and went out of hand. People were curious, wanted to know what is it. So you can't suddenly pay for that kind of scale unless you have the pre-planned stuff. Right. So before you even go to the scaling on a multi-cloud environment and with native components, of course, some of the decisions that you make here is going to hurt you in the long run, right? So I give you an example of a native service. Let's take Google App Engine, right? So we had one specific deployment of a customer. So the customer came to us and they said, "Look, I'm in serious soup. I have a lot of traffic coming in. I'm not able to scale the App Engine." So turns out he took a default template on App Engine. That was a 2 GB instance. That's the default the App Engine recipe that he used. So the way that he deployed his Firebase events and so on. So what was happening was every 1 minute it was spawning something like 10 instances. He had his limit of 10. So he was spawning 10 instances because that single box was overshooting on the load, that 2 GB RAM box. Right? So he was spawning 10 instances and deleting 10 instances at the same time because 10 is the limit, like you said on the app. So effectively no traffic was being served. Right? So basically, like if you have a small box which is not able to handle some unit of traffic, no matter how many boxes of that same configuration you put, you still cannot handle your scale. Right? If you, let's say you need 4 GB RAM box to run your some containers, some Java app with so much of memory for JFX and so on. If you are not able to run that on 4 GB and you have if you're able to run that on 4 GB and you have a 2 GB instance, even if you have 100 instances of this 2 GB, it's not adding up. It's not scaling. Right? It's that Hindi wala joke, na? a family was crossing the river, right? So the average height of the river was 5 feet, right? And the average height of the family was 5.5. Okay? So when they crossed the river, only one survived. So out of 4 people, only one survived because that one guy was 7.5 feet. So on the average calculation, he made them above 5 feet, but they were all like 4.5, and so on. This guy was 7.5. That's a very popular joke. So point is that unless you have that unit of computation which is able to handle certain traffic, you will not be able to scale. So what is a good box needs to be determined first hand for scale. When you're talking about how much of RAM, how much of IOPS, how much of CPU, how much of network capacity you need on that. So those have to be decided. And the second thing is you need certain percentage of overcommit on a per box basis. I'll explain why. So let's say you have a 4 GB RAM box which is running some X and Y services. Now let's say you have a threshold of some traffic or some load, at which point you decide, okay, I'm going to fire up another instance on my native service. Right? Now the challenge here is no matter how fast your orchestration engines are, right? You still cannot get a server up and running in reasonable amount of time. Right? For example, my friend here at DigitalOcean, they say 55 seconds. That's how typically it takes them. It's actually very fast. But then that's just the instance for you. Then you have to orchestrate a service on that instance, make sure that it is added to the load balancer correctly. Of course, this is all automated, but there's still a finite delay in getting this thing done. Right? Even on containers, if you're doing all this on containers, you still have a challenge that there will be a few seconds of delay before which your containers will start accepting traffic and actually start serving traffic. Right? So the choice is to just do overcommit for that incremental traffic rather than going for a new machine. So case in point here is if you have 4 GB RAM, just do 5 GB or 6 GB. Right? Anyway, the cost of the infrastructure in IaaS world is so cheap. Right? If you're doing 4 GB, just do 6 GB. Whatever that incremental traffic is there, handle it on the same box instead of going through the overhead of firing up a new box, orchestrating it, adding it to the cluster and so on. Then the third point is obviously network planning is super important. You have to get your security strategy right. Okay, how is my tiered architecture in terms of, well, let's say you have a fairly decent deployment, so VLANs kaise aayenge, then what's your outbound bandwidth, what's your incoming bandwidth and so on. Because if you can't change these things on the fly, right? Let's say you have a fully secure system which is like behind the dam and so on, and your outbound traffic is only so much. During times of a crisis, you can't change this altogether without too much of trouble. So if you know of a recent instance last year, HipChat went down because their NAT gateway bandwidth on AWS was not up to scratch. So they had like a lot of authentication failures, this, that, over an 8-hour period. Then obviously Amazon helped them scale that particular part. But it's not an easy thing to do. It's not something you have a switch, you click that and then your problem is solved. So it's important that these 3 things are solved before you proceed on your architecture. How will my containers look, this, before going live, fix all these things. So if you're doing containers, figure out what's a good container size, how much of vCPU, how much of unit of RAM you want to give, figure that out. What's the overcommit and how is the networking, whether it's an overlay, whether it's like whatever you're doing. Basically so there are like a lot of studies which say if you're not doing dynamic changes, don't do service discovery for things like BB and so on. Right? So a lot of such considerations for network are there. Right? Because your master key is not going to change any often. So if you use a service discovery, you have to assign a DNS name, and for every request that your app is making to the DB, there is an additional DNS lookup. Right? So that kind of planning is super important. I'll give you one more case. So there was one major app bank who was essentially doing like a lot of updates to the customer. So one of the things they were doing was weather updates. Right? So what they were doing was they were looking up AccuWeather and doing like a wholesale update for all the weather regions for everyone who has an app of that particular company. So So when they were doing that weather update, their network was not choking, but the entire DNS lookup were choking. Right? They were doing practically millions of requests per minute. So we had to step in, make sure that then we set up something called unbound.net, which is like a very, very lean DNS service provider, does millions of requests per second without too much of delays, no latencies as such. So those kind of DNS infra, NAT gateways and all that should be set up before you start even your scaling discussions and so on. Right, and this is one more question before we go to the nitty-gritties of the scaling challenges. When do you scale? So the typical metrics that used to be counted for these decisions, like your CPU being high, your load average being high, and so on. So those are not the only factors, right? So there are like a lot of times when all the metrics that you have in terms of your monitoring systems, like let's say your Nagios or Zabbix or ZenOS or whatever you're using, all of that will be fine. But then your users will start reporting problems, right? Your customers will start reporting like various problems, like some gateway timeout, this, that, and so on. So you need to make sure that this particular math is tied into your scaling algorithm, right? So basically monitor final text on all entry points, right? And also monitor service issues for all outgoing services, right? For example, we are in PayU, right? So one of the things that all of us startups use is a payment gateway, right? Now, how do I determine if my payment gateway is up and available and running and what's my transaction date? So unless I figure that out, I cannot go and solve some of the other problems, right? It could be as simple as, okay, I don't have enough threads to do enough lookups to the payment gateway folks, right? If I'm serializing too much, then the number of transactions in a particular time frame for any payment gateway will be low. So I have to increase the number of threads, do parallel transactions, and so on. So all entry points and exit points need to be monitored for these kind of service failures. So merely relying on your monitoring systems is not enough to do scale on a multi-cloud environment. And obviously, ETFP and so on are still a problem, which is why everyone, right from the AWS and GCP to DO and all that, have a data center in India, right? Otherwise, all of them would just be in US and so on, and we would be continuing to have 300 milliseconds latency and accessing our mid pages, right? So latency is a real concern. PTFP is an even bigger concern. So make sure that you have this figured out before scaling. Right. So two types of scaling. One is reactive scaling and proactive scaling. The proactive method is actually very simple. You have an upcoming sale coming in, and you say, look, hey, my cloud provider, give me so many additional machines, right? And take a 40% overcommit. If you have 10 boxes, get 5 more, and essentially run through with that sale and take them down, right? So then the assumption here is that, for example, if you're in a data center, you have bare metal delivery of servers, that can take from minimum to a few hours to a couple of days. Assume that you have like a lot of cold cache problems, so you cannot, even if you deploy a server in the middle of the night, it will still take time to start taking all the data, typically of your backend system, your DB masters, and so on. So even if I have a ready server, as long as my data is not replicated, let's talk about a slave, right? As long as my data is not active from the master, I cannot put that into production. So those kind of things require a bit of planning, and you have to be a bit proactive. Now the other paradigm is basically like what do you do on the app side of things, right? So essentially reactive, whenever traffic hits, if you want to do that, so you need like basically a lean infra, which is your load balancers, your data stores. That is all you need as the fixed part of your infra. And then the rest of the app and the APIs and all that are all dynamic. So what you do is, you assume that you have a rapid provisioning system where you have a very fast clip of provisioning. Typically containers fit that well, because your virtual machine, no matter how fast, it will still take a minute to fire on an average. So containers are the fastest because you can get it in as simple as like a couple of seconds. You can fire up a container if you have your a native hybrid. So and it is ideal for web traffic because that is where most of the flexibility is there. And containers are also a very good tool if you are doing like a lot of CI/CD stuff, right? If you're doing CI/CD where you're doing releases every hour and so on. So the easiest way to do that without incurring like too much of outages and making sure that all your parameters are alright is to do it with containers. So what every container algorithm will do is fire up a set of containers, make sure that the traffic is failed over to that and delete the original set of containers. Okay. So and of course, like I said in the few minutes back, you need numerous data pipelines. So with containers, you need like a lot more intelligent algorithm to feed it rather than your load average, CPU utilization, and so on. You need more stuff like what's my average response time. If that is going slightly higher for the API, then I'll fire a few more containers, right? So okay, and also understand what cannot be scaled, right? For example, your DB master cannot be scaled without downtimes, no matter what it is, right? Let's say your sharded systems you can't scale. Of course, there is a strong line of thought which says never do sharding, but even if you are sharded, you cannot scale that in a jiffy, right? It's not that I can add 4 more shards just like that. You still need to repartition your entire data sets and so on. So typically your data stores for most parts cannot be shared unless you are on an environment like Bangalore. But still the syncing part, all those stuff take time. Right? Somebody just buzz me when I am out of time. Okay, so let's look at the typical cloud native architecture which can be replicated in any cloud environment. Right? So that's one of the things that you have to figure out. Make sure that my advice would be not to get tied up into any single particular cloud by way of using like a native service itself. A native service is, for example, if you're using SQS, right, a standard queuing service, instead of let's say your Rabbit MQ or whatever that is cache you are using for queue building and so on, then you have a real trouble if you want to migrate that to another cloud provider. Right? So this is one simple example. You have your entry points, your NATs, this is your web layer, you have your own APIs, logs, these are all your data stores. So this is how a completely independent architecture on any public cloud looks like. And this can be replicated anywhere. Name any public cloud, this can be replicated. Right? So this is how you need to design infrastructure when you are wanting to do a cloud native. Cloud native is it's a slightly a twist of that term. So cloud native means like you want to be on a cloud, but you still don't want to be stuck to a cloud. Right? So there is a minor differentiation that you have to be cognizant of to make sure that there is no component that you use for most parts unless you have strong reasons to do what you are doing. For most parts, be independent so that this entire workload can be like, it can be your bare metal boxes, it can be AWS, it can be Devops, it can be Azure, GCP, anywhere. So this is how you design your stuff. So I'll give you one example. Then I'll take you to the containers and so on. So let's look at this. This is your, so there are some part of the network, like I said, which cannot be scaled, right? And this is one part. So your core firewall setups, your core VPN infra, your NAT gateways, those cannot be scaled. And even your stuff like your DB masters and so on. So here the priority is reliability. So you can't play around with your data sets and so on because there's a real chance of any corruption happening which will throw your site offline for a long time. So low rate of change, high cost of change because these are big components and the cost is involved in terms of not just the cost of the instances but also the cost of the actual transmission and downtime itself. And you can't have any disruption, right? So if you muck around with the firewall, your entire portal is down, your entire site is down, your entire app is down. You can't do that. So, but then there is an app-specific network where you have the APIs and so on, where the components are treated as expandable, right? If you have, let's say, 5 web servers, one of them going down, it's okay. It always happens. It happens all the time. So you design your network accordingly. Okay? There is no single point of failure, and any deployment is fungible. Right? Any box you have, any containers you have, you assume that my single point of failure is not there. Right? So once you have that, then any part of this can be taken off. Right? I'm not sure how many of you have read about this interesting approach to this by Netflix. They call it the chaos monkey. A lot of big infrastructure providers or setup these days do that. So what chaos monkey does is, let's say you have 1,000 machines. It will go and randomly turn off the few machines. Right? The idea is that even when that happens, there should not be any service delivery issues. Your app should be fine, your entire, whatever you're doing, for example, Netflix is into streaming, right? So their entire network should be fine, irrespective of what some random bot is turning off and turning on. Right? That's the idea. So here, you assume that you have designed an infrastructure where your app, your services, your APIs are available, and there's a high rate of change. High rate of change as in, for example, if you take here, you're not going to upgrade your MySQL from 5.6 to 8 like overnight. That's like months of efforts and so on. But you are going to do daily deployments in your release cycles. Right? Every day there will be a feature release, every day there will be a bug fix, something or the other is going to happen, keep happening here. And the cost of the change is low because we are using expendable instances. A lot of people use spot instances for this to reduce the cost of the deployment. And the disruption is, the tolerance for disruption is high simply because you are assuming that even if 10% of my infra does not work, I am still fine. Right? So I'll just take you to the next a couple of slides which tell you how do you design a total multi-cloud architecture. So this is one open source project called Venture. I'll skip some of the simpler parts. So essentially what it does is gives you user management, right? Gives you handles like all the major container orchestration frameworks like your resource, Kubernetes, and provides you infrastructure services on top of it, your service discovery, your DNS modules, your load balancers with the proxy, and it could be either bare metal or it could be any of these public clouds for that matter. There are like a bunch of others. So what it integrates well with your CI/CD and so on. So this is like something that you can refer on your own, but I'll take you to a more interesting case. So let's look at this. So here I have an app which is running on 3 instances, and what do I do is I essentially design it in such a way that I can decide which part of my infra can go into which cloud, right? For example, I have a 3-machine cluster here, so 2 of them are in AWS and 1 of them are in Google. So I essentially have my Redis, Postgres, and this is split across here, right? So the idea behind this is that cloud-specific workloads can be leveraged based on who is providing the best feature for that, right? For example, Google has a lot of fancy machine learning APIs and boxes are optimized for that. So a lot of people are using them for GPU and stuff like that, right? Although there could be some other public cloud which is good for something else, right? So you leverage based on what is the good feature in each of the public cloud, and you design your container strategy with Rancher. So essentially, just to give you a brief, you can set things like tags and labels, and you can create your templates where you can decide which of your workloads will go into which of your clouds. So this gives you a rough feel of what you can do, and essentially all of this is load balanced. And one of the good things that is happening is that in India at least, all of these big cloud guys are in, for most parts in Mumbai, right? I think Devops is in Bangalore, but your AWS, Azure, GCP, all of these guys are in Mumbai. So between them, the latency is of the order of like 3 to 4 milliseconds between all these cloud providers. So it's not like it's in different continents and so on. So you can do even your web app application spread over multiple cloud providers as well. So then you go purely cloud native, where you're not beholden to any single public cloud, and essentially your cloud scales across multiple cloud, and whoever is giving you the best possible price performance ratio, you can migrate your workloads to that. Okay, so summing up, like I said, this is a small wordplay on cloud native. Of course, this is cloud native. So cloud agnostic means what I'm saying is don't tie yourself in knots in any particular microservices of a native cloud. Right? Be on the cloud, but don't use the native services. And essentially, your app is agile to be moving around to different clouds. Use microservices, containers specifically, and this can give you exponential web app scale. If you want to like really get traffic, really handle traffic when you are listed on Reddit and stuff like that, you really need to be on microservice and so on. Essentially have new age metrics. Don't rely on your typical load average, memory utilization, and so on. Instead, define your ELK pipelines, Elast alerts to decide when is scale going to kick in. And my prediction is in the next couple of years, any web scale app which is serving user traffic to the people at large would be multi-zone and multi-cloud. Right? So multi-zone means like you're typically doing it for DR purposes and so on, but essentially multi-cloud is the deployment that we envisage in the next couple of years. It has already started happening. So we see a lot of multi-cloud deployments where people are using frameworks like Anchor and Spotist as well, where they're distributing their workloads across multiple clouds. So that is where we see this going. Okay, I'm done. So please let me know if I can clarify any of these.
What is the ELK pipeline you talk about?
ELK pipeline is a Elasticsearch, Logstash, and Kibana. Right? So what it does is it takes all of your syslog, any log that you do, which is in syslog format, let's say. Let's, for example, your load balancer logs, your application logs, and so on. And you can define regular expressions after that. Once it's in Elasticsearch, define regular expressions, and there's a tool called ElastAlert which integrates into this ELK pipeline, where you can decide with regular expressions, okay, look, if I get so many errors in 1 minute, then please send me a Slack alert, right? So that is minimum. You can also make it do complicated stuff like firing up a new machine and so on. So when I say ELK pipeline, it's just a monitoring pipeline which is built on your Elasticsearch, Logstash, Kibana, the ELK stack. Any other questions? Does that answer the question actually?
Yeah, I wanted to know it.
Sure. Alright, I'm fairly active on Twitter, so let me up anytime you want to get in touch, and happy to be here. Thanks, guys.
Thank you, Imran. Our next speaker would be Vivek. Just to let you all know, we collect the puzzle sheets after Vivek is done talking, so you can just keep it ready on the side. Thank you.
So, good evening. Good evening. Good evening. Cool. Fine. So, pretty interesting for me. So can you guys tell me what this picture or the snapshot represents? It's okay, we can have a discussion. We are very small here. Go for it. Anything. Okay. So these are the microservices, interactions raising of Uber. This is the number of microservices Uber has today, probably even more. This was even before Ola, Uber, I think so that they will have more. Right? So these are the microservices, and this is the raising graph. That is, these are the interactions which Uber is having today. Okay, so that's pretty complicated when you think from the scale perspective, right? So today's discussion, what I will not be discussing is the architecture. Okay, so obviously I'm talking about the open tracing, I'm talking about acres, but I'm not going to talk about acres architecture and other stuff because it's obviously available online. I'll give you links. You can go back and read stuff. Okay, and phrasing is basically developed by it's actually implemented by developers. So it has both dev and ops component into it, but it's basically developed by developers, consumed by ops and developers both. Okay. Cool. When I'm talking about tracing, when I'm talking about microservices or anything else, you think from we have more than 50 services interacting with each other. Just don't think that we have 5 services. Why do we need a tracing? Why do we need all this stuff and all those stuff, right? So think from the larger perspective, think from the scale perspective. Okay. So just to give an introduction to myself. I am a developer advocate at Big Solution, and previous to that, I was heading the Devops and QA at Blackbird, and I was working for HCL for a big data projects in Australia, and I was part of IBM India Software Labs for more than 8 years. Okay. So, what is microservices? Anyone want to go for it?
Like when you divide big service into smaller modules and then you have a wrapper which hits and it basically responds of yours. So it's just like a Wi-Fi connection.
Perfect. Let me. So, okay. Will this help? This example. Say, for example, we have a marketplace and we all use Flipkart, right? So I've taken this example because we can relate to it, right? So there are certain products, certain orders, which cart and messaging and accounts, and a code push to product will not hurt the order management system. A code push to cart will not hurt the the messaging system. So these are different individual services solving different problems, right? So and it has its own database, and these are all connected with a queuing system in between, which is actually managing the messaging between each other, and it has its own database. These are all decoupled, so there is no coupling. So basically, this is a simple example of a microservices. So when this comes into picture, what happens when there is a latency and somebody is trying to book something or trying to access the billing and the page is not loading and other stuff. There are various services. It touches various services when you try to access something, right? So when this is happening, as of today, what we follow as an analysis is, or at least from the latency perspective, is we do log analysis, right? If there is a some issue you see, some spike you see in your metrics, in your what do you call the, the Prometheus and other things which you use for metrics. Once you see that, you get you do log analysis, but think from the larger perspective. Okay, there is a lot of services and there's a lot of logs being generated, and looking into these logs obviously is time consuming, and it is not always correlating. Just imagine from Google perspective, there is so many interactions happening and so many logs being generated. If somebody has to figure out the latency issue and fix a latency issue and fix a particular database latency issue, how difficult it is to trace back all these stuff, right? So this is our first option, right? And the second option is obviously metrics. We obviously get that at this point of time there is a latency, there was an issue in your product, and there was some delay in the response and other stuff. But even then, you are not at the core of that particular request. You are not actually looking at that particular request, right? So to do that, and again, there is not, if the more number of services gets added, you typically end up seeing a lot of problems. And I'm just talking about microservices problems here. So whenever you start using the microservice architecture in your applications, there is new problems definitely arises. Is that root cause analysis? When you have to do a root cause analysis of a particular request, why the particular request failed, why there is a latency in a particular request, it's very difficult because it touches more than 15 to 20 services to actually serve a particular request, right? So transaction monitoring will become a difficult, right? So there is a lot of transactions. As I told you in my previous slide, there were a lot of databases, right? Each one had different databases. So each have their own transaction commits. Okay. So when there is a request coming in, these transactions hop from one service to other service, and the commit actually is a backward commit. It's not like it's going to commit as soon as a service gets pushed to another service, but it actually goes to the end of the request while serving the request back to the the request provider. It actually starts committing into the database. So transaction monitoring, where it failed, where exactly the latency came in, which database actually is affecting, is what becomes a difficult process when you use microservices. And again, obviously the service dependency. There is a dependency between services. Service A is always dependent on service B. It is waiting for service B to provide that information to serve its own request, right? So basically that service dependency becomes a problem, and obviously performance and latency optimization is pretty difficult if you're not using a kind of tracing a particular request, right? So context is very important thing, right? So let's take an example, a simple example. You all use Book My Show, right? So Book My Show is having dependency on PVR to give that information to while booking a PVR forum or a PVR at Orient Mall, right? So when you request something, it actually sends back the tickets, right? So there is obviously a dependency on each other, and in what context this dependency was, on what context the discussion was happening between two services is not known, right? So the context between these things, you don't have that information. So very difficult. I'm talking about external service. What about internal services? You don't have the context at all. Why did products is talking to cart? Why did why for a particular request or product is talking to an order management system? You don't have those contexts, and when it fails, in what context it is failing, you have no information on these, and it's very difficult to get these information via logs, right? So what is the solution for this? So the solution is basically to go ahead and trace each request which is coming in, right? Each request. There is a request, there is a request gets started, if you start accessing a building, and it should actually end unless and until the building request is actually served, right? So it actually you need to serve, you need to see where all it does, what all happened between these services. So the solution was crazy. Okay, so I'm not telling that we will be moving out of log analysis and monitoring. We will be doing that, but this is a new way of optimizing your code, knowing what your code is doing in a distributed system, understanding what's happening in your code, and probably fixing those problems in terms of not just latency but also in various other circumstances. Okay. So these guys actually came up and built one kind of tracing systems of their own. Okay, so Google had their own, and Zipkin came up with their own, and like Twitter, which is the Zipkin stuff, and Google had one more, which is called as static trace. So basically, everyone had their own way of solving this problem, right? So but they had a very core system. That is, the three core things which they always had was code tracking. They were tracking the code, and they were storing what was happening in the code in the storage, and they were able to query for that information. So all three of these basic things, these guys were doing. Okay. But it had problems. What problems it had? So obviously, everyone designed their own system to solve it, and the logging and metrics and tracing and interoperability. They were supposed to be talking to each other. They had like logging system. Logging system is same in tracing as well, and also in your application, which is time series logging, which is the latest one, right? If you're using containers and other things, you will be using Prometheus and other things, InfluxDB and other, which is very time series logging system. But these are logging systems are same. But the problem was it was not able to talk to each other, and obviously the process like A service and the B service had different logging products itself. One was using ELK, one was using different product like the Prometheus. So they were not able to talk to each other and other stuff. You can see that. And obviously there were vendor logging and there was no standards and other stuff. So this is a typical problem, right? So what cloud native did was they came up with something called as open tracing standards. So they came up with a standard. That's it. So they built a standard for this tracing events, and it just makes sure that if what's happening with the particular request, from where it is coming, where it is going, and what is the transaction, what is the type of transaction. So it actually records all this stuff. So basically they built a one standard so that the libraries can be shared between different services. So let's take an example. Say your service, you are using a tracing API, and there is a shared library which you have, that which you can share it with any other service to give the information. And there is one more service which is not your service. So basically, like the same example, right? There is a book my show and there is a PBR, and you don't know why it failed or what was the problem with performance. Whether my system was slow or is it the PBR that was slow. So to get more information from the PBR, the services, so it shares the information. For sharing of information, there needs to be a standard way of talking to each other, right? Otherwise, it's very difficult. If I am talking in some Italian language now here, you will not be able to understand. If I am talking in English, then you are trying to catch up with what I am trying to tell you, right? So this is the same concept. So Agile is built on this standard, and pretty simple. So what it does is it is actually making sure what is your code doing. So basically, for each request, what your code is doing. Okay, for each request. I'm not talking about there is bunch of requests coming in and stuff like that, but I'm talking about each request. You'll see a demo of that, and of course, it actually tells you what is the pattern between these services. What is the transaction differences? Which service actually talks to which service? The diagram which I showed you, right? There was the Uber graph diagram, dynamic graph diagram. So tracing from one component to another component. So basically, there is different components ops which happens. So tracing the whole transaction is what Eager actually does, and obviously Eager has a pretty good architecture. It works on Elastic, it works on Cassandra, it has collector and other stuff. It is built. Architecture is actually pretty interesting to read. I'll share the link. You can go back and read about it to further explore stuff. Okay, so just to give you a complete overview, we had some e-commerce site, and you did some stuff on that site, and you actually touched upon service A, service B, service C, and then you did some transaction. It got recorded. You did some transaction. So when you did something on service A, it records on service B, records on service C, records, and then the transaction is also being recorded. So basically, this is Eagle, which is actually recording all the transactions, all the requests which you do, and then it actually stores it in a database, and you can access it and perform queries on it to figure out latency issues, to figure out if there was some failures in some particular cases and why it was failing and all this stuff. So it comes up with some of the concepts. Okay, some of the concepts is we call it a trace. We'll talk about trace later. First, we'll talk about span. Okay, span is nothing but for each request and each interaction is called a span. Okay. Each request within for a particular service is called a span, and it has so many details. That is operation name, start, end time, and there is tags. So you can add tags. So basically, all these things are added by developers. So you can add a tag. So when this transaction is happening, you can add tags to it, so that in future you can actually trace it. Okay, and there is logs. Obviously, it is timestamp. So Prometheus and other stuff can actually read these logs and give you more information. And there is packages. Packages are nothing but when service A is talking to service B, it is actually pushing some context, some data. Say for example, you're actually trying to request a billing information. So you cannot request billing information without authorization, right? So without you being authorized, right? So basically, you log in, you authorize, and you request a billing information. It still requires that information of authorization. So for authorization service, account microservice is actually talking to authorization service, telling it to package is pushed, authorization true or false is sent to that service, and then that service actually takes care of the providing the information of billing information, right? So So this package is nothing but it is giving the metadata. It is pushing the information to the another service. Telling that this is the context. This is what is happening. This is the package from this service to other service. And of course, references. The services can be can be checked off, or it can be follows from. So basically, a particular child of a particular service, or it can be a following service. Like how I showed you following service in the previous slide, it could be a child of service. So this can wait for this to complete. So basically, there is mix and matches. You can actually go back and read about it. So for a complete request, it's called as trace. So trace is collection of spans. So basically, you'll say, for example, service A, B, C, D is there, and the transaction is touching all these services. Then span 1, span 2, span 3, span 4, right? But collection of this whole thing for a particular request is called a trace. Okay. So let's take a simple example. I'll just give you this example and then show you some demo. So just think from there is a request coming for an authorization to check for the billing, and then that these are spans. Okay, these are each one is a span. Okay, and it's a collection of this span is called trace, and it is obviously timed. And there is authorization. Once it's authorized, it goes to billing. Of course, the backend is sent to the billing, and billing is actually doing the resource allocation. If there is no resource, then the container is spun up and storage is added and script is run. So basically, a lot of things happen, and then it serves the request back to the the client, which is actually starting this plan. Okay, so this is a simple example of a single trace. So I'll do a brave, so it might fail as well. So I'll do a small demo so that we can see more of this. Okay. You can see that. So I have hosted installation. Okay, just logged in. So I'm just spinning up a either Docker image, but it has a lot of components. Right? It is having a database component, it has collectors, client, and other stuff. But to do a demo, I'm just running a Docker image. Okay. Just run an example. This. So this is a simple example. Okay, this is having 4 different services. Okay, and it has. If you notice that there is a client here, which is having the session ID. Okay, you can see the session ID here, and this is four services. So basically, it's not an Uber app. So basically, we are trying to put a cab here. So from different locations. So these are representing the locations. Okay, and say for example, I'm going to click on this. It is dispatching car. And there were two requests which was served, and you can see the latencies, right? This had some latency, and this had some latency, and this is not even served, right? There is a failure of this particular request. So when you have to do that, right? When you are now you don't know your customer actually tried to do something and whether it got failed or not, and why did it fail? It's very difficult to figure out. And there is latency information which you can pick it up from your metrics which you enable. But this information which is on the acres. Sorry. So this is the acre UI, okay? And there is obviously dependency chart which I was showing, which show you the graph. So for the three requests we did, right? We did three requests, right? For which one failed to clear. So for that, there is two requests, right? Was microservice, and there was an interaction with Redis 27 times, and there was interaction with something called as routing algorithm, which is designed for 20 times. So basically, there is so many transactions or interactions which has happened in between. I mean, this is just a demo of how interactions happen, right? So there is for three requests, there is a lot of interactions which has gone through. Okay, and let me go back to this UI. So basically, I'll show you praise. So this praise got failed. Okay, this was one of the praise which we clicked, and it has failed. And this is the span. This is the request span, which is the it shows you the complete information of the complete request, but you can see that there is certain spans in between which has triggered. That is, this is talking to customer microservice, or this is talking to the customer one, and you can see that why it failed. Okay, so here the transaction failed because it could not acquire lock, right? It could not acquire a lock for this particular transaction. So you can actually trace it, and you can actually see what query it done to acquire that lock and how to fix these problems. And you can actually see some of the things like tags and all those stuff. The tags, that you can actually create those tags, and you can create from what is this kind of interaction and other stuff. And let me go back, and you can see this from here. There were two failures, and there was two which got through, right? So there is, now you can see that this particular trace has taken so much time, and you can actually go to each trace and see what all is happening in that particular request. So it is talking to Redis, and something failed in Redis. So these are spans. So each span is here. You can see that, right? And of course, they say not to read this particular, information. There are obviously there is patterns to do to it. There are different kind of patterns, and each of these represents different. Each of these colors represents different things, and you can see that if you click this information, the information for this particular why this driver is this one get driver is failing, you can actually see what is happening here. It requires time down. So basically, you can fix that. Go back and fix why that Redis is giving you request timeout for these kind of services, these kind of requests, and you can actually tag that information and then trace it back. Okay, so this is the basics of tracing. So you can explore more. It's available. You can explore more. You can build it. It's basically built by the developers. Developers have to use the plugins and packages of Bangalore in different languages it is available. So whether it is Go or it is in whether it is in Python, so Node.js, so you can just implement these things on your phone and actually play around with this to figure out the more latency issues and other stuff. So this is what Data is all about. Let me go back to the slide. So here is the information. So you can, the repo is there, the code repo. So you can actually do some stuff on the repo you download and build it. And there is even architecture link is here. And I'm just putting out the framework, which is more important. Like if developer wants to develop this, you need to understand the framework. So the link is here, and some of the concepts and technologies which I spoke, you can actually go back and do more research on this stuff. Okay, and that's my Twitter handle, and you can provide the feedback of this session so that even I can improvise this session to a better session next time if I'm giving it to a different audience. So, if you have any questions, I'm ready to take questions. Otherwise, I'm still here after the event as well. We could discuss more. If you want to discuss more on different topics here, we could obviously discuss on that as well. Any questions?
Diagram option available. So one transaction, some scenarios, Java is a little bit to play back the same scenario.
I mean, no, there is no playback, but that's a very good solution. In fact, that's a nice thing to play back, but there is obviously difficulty in terms of building that out. Obviously, there is challenges to build a playback of that request, but as far as I know, there are playbacks for if you are using UI, if you are using something in mobile app, there is something called as app text or app sense or something is there, which actually you can play back what user was doing on the app. So people can actually see what you are doing on the app.
What is that?
I'll see you. You just ping me on Twitter or on my LinkedIn. Any questions?
Do we have any more questions for Vivek? Okay. So before we call upon Kalyan, can we just have your cover sheets? Just give it to us. He'll be around. Don't worry. So we have the networking session. You can talk to him there. Thank you, Vivek. Over to Kalyan now. So to you, Mohamed.
So hi, I'm here to talk about this particular presentation to be on a scale where somebody wants to understand what a DevOps is and how do you apply it to the cloud or whatever it is, container world, whatever technology world that you talk about. So it's pretty much going to be a discussion where I would like to take questions in the middle because since I'm the last speaker, I think I have the ability to take the time. So you guys can actually have, and it's pretty much going to be certain fundas that a DevOps team should technically solve, and we will see how I could take some examples, and you guys could ask questions in and around whenever you guys have doubts on it. So this is pretty much intro session. There is no specific tools or something that I'm going to talk about, or specific protocols. This is more on basic fundas that DevOps team or a high reliability engineering team should, for that matter, solve. So could I know my audience before that, like what percentage of people are from the DevOps background who actually work as DevOps, or are you guys at devs? Could you just give me? So could I have a rough idea like what brought you guys here for the talk? What is the what do you guys think that would be a takeaway from the talk?
I don't much more DevOps. So I don't go much deeper into those naming conventions what DevOps is. Otherwise, we just do whatever is needed for deployments and managing the stuff.
So I get it started. So whenever you guys have any questions, ask me, or else I'm available for discussion. So a brief about me: I work as lead DevOps engineer at Meter.net. Meter.net is an ad tech company, and we are part of the Direct umbrella. We went through an acquisition recently. I work as a DevOps engineer at Meter.net. I'm here for 6 years. Before that, I was in college. So this talk is going to talk about certain philosophies that a DevOps team should satisfy. So I'll just run through all my slides and again come back. So a DevOps team should take care of automation part. They will be the architects in your environment, in your company, and they will be maintaining the infrastructure. They will secure the infrastructure, optimize the infrastructure. They troubleshoot the infrastructure and help the developers in troubleshooting, and they take care of the deployment part of it. So this is pretty much what DevOps, these are all the philosophies that a DevOps team should ideally satisfy. So if it's a dev also who is doing the DevOps work, whose work satisfies all these requirements, then he becomes a DevOps. Or he is a person who is doing both hand in hand. So this is a technical, this image is obviously stolen from Google Image. So this image is to show how automation is happening in productions. So all the production assembly lines are going through so much automation. There are robots which are fitting parts and stuff. So infrastructure deployment also has gone through a lot of automation. So how many of you guys know the sysadmin era? Since there are a bunch of people, if you could raise your hands. Sysadmin era. In your college, there would be a sysadmin guy who is managing servers, and he is the person who, in my college, he is the person who blocks pen drive access to the systems, or he is the guy who has the root access, the network drive access, wants network drives and stuff, who gives out users during lab examinations, who gives out separate users for lab examinations. So it all started even in production environment as sysadmins, and since academics is usually stuck at the old age, they're still stuck at sysadmins. And what a sysadmin does, a sysadmin is a person who probably takes care of setting up servers, installing software on the servers, and making the requirement, could it be a product developed by the devs, up and running. So that's what a sysadmin's job is. That's what a DevOps job is. That's what a site reliability engineer's job is. It's just the way they function has changed. Sysadmin would be a person who works with bash scripting and Perl script, because he dealt with max of 100 servers, and he thought automation could be a bunch of shell scripts, automation could be a bunch of Perl script. So when a server comes up, somehow the OS has been installed and then the shell script has been run. This shell script installs whatever package it is necessary, and this shell script actually does start the service, whichever service has to be started. The shell script can actually pull and do necessary stuff. Then there was a pre-cloud era, probably the time it was actually 6 years before or 5 years before when I just entered. So that era was almost coming to an end when I entered the field. So during that era, what was happening is people obviously can't install operating systems manually. You can't do disk partitions manually. You can't go and install Apache server on hundreds of your web servers. So then they came up with a lot of things. They came up with automation on OS installation. Like there are a bunch of tools available for it, which most of the startups today will not use because they are on cloud. They're not dealing with the data center operations. There is no need for you to automate OS installation. So when I'm talking about OS installation when a server is running, because the server is just a box, it has nothing on it. So it automatically comes up. It picks IP from DHCP. It picks OS from network. Then it copies the OS, installs the OS on its disk. Then it comes live. So there are a lot of tools, fully automated installation tools called Cobbler, and a bunch of tools available to satisfy this. Then people actually wanted software that are installed on boxes to also be automated. So then there came a bunch of tools called config management tools. These tools are still in prevalence. A lot of companies use it, like Ansible, SaltStack, Puppet, Chef. So these are the pretty much commonly used config management tools. So what is the use of config management tools? They are supposed to maintain a state. The state as in the system should have Apache installed. Apache should have XYZ config files, and it should always begin Apache running. So on each run it sees, is the file same as the file I'm supposed to serve? Is the service running? And is the package installed? In a proper order. So package should be installed first, then the config should be served, then the service running should have been happening. So this is what the pre-cloud era is. In the pre-cloud era, there are started happening a lot of virtualization tools like VMware ESXi and KVM and Zen. So a lot of such tools start appearing. So these tools actually started doing a bunch of stuff like they start. So technically, most of the soft hardware, if you see, is like 16 cores, 32 GB, or 24 cores. So in a technical scenario or a microservice infrastructure, each service does not need 16 cores. So people actually felt they are not taking the return of investment on the hardware. For each hardware that they buy for 16 cores, they see just 4 cores being utilized or 8 cores being utilized. So they needed more resource utilization. So if you run multiple unrelated services, then what happened is there has been more side effects. Like one guy upgrades Apache because he needs an upgrade Apache. The other guy can't upgrade Apache. So for that resource isolation, the VMs became like a boon. So the VMs started, and after the VMs came in, the VMs were there since long, but the VM technology of para virtualization and full virtualization with hardware supports came in 2000s or 2002s, and got widespread adoption after this cloud era came in. But AWS is technically just a VM you guys are running. Google Cloud is just a VM that you guys are running. Everything is a VM, or else you can run a proprietary VM at your data center, which could be a VMware, or you can run OpenStack, and you can take your hands dirty with actual KVM on your data center. So it's the VM technology came. Then on the post-cloud era, people also, the common problem that a DevOps guy would face is, this works in my environment, in my dev environment. This is not working in the prod environment. So replicating prod environments, technically what earlier they were doing is they gave AMIs, something similar to Amazon AMIs. You have image of your virtual machine, run the same virtual machine on local as well as run the same virtual machine on a development environment, run the same virtual machine on a prod environment, everything. So this is probably what people did. But the virtual machines are bulky because they had the whole OS, whole kernel and everything. So then there came something called containers. So the containers actually had an overlay file system. So the image size is really small. So anybody can just do a Docker code, run it and start. So this is how the automation has happened from a manual installation of system. Today people doesn't even know where the system run. It's run in some cloud, and you have a schedulers on top of it which runs containers, which could be Kubernetes or which could be Mesos. So there is enough abstraction done right now, enough framework has been put in place, and so this is one of the philosophies your Sysad or a Devops will know how to automate the infrastructure, because automation makes sure the provisioning time of the infrastructure is faster. Since so much automation has done, we have the luxury right now to talk about auto scaling. Earlier, like even a decade before, auto scaling would be a myth, because if somebody says how do we do auto scaling, there would be no enough hardware available in relation to auto scaling. Today, auto scaling is based on assumption that there is an infinite supply of hardware that is available on a cloud. A decade before, people would have to put a purchase order for a hardware. The hardware has to come, it has to be racked, it has to be done. So automation is one key thing. So yeah, so it's like a decade before, people treated their servers as pets. Like they have host names, they remember servers by IPs. Now they treat servers as scatters. Like you spawn instances as spot instances. You know the instances will go down. Then if the instance is about to go down, you have a replacement server. There is no naming conventions for your servers. That is more matter now. You need at the end of the day X number of web servers running, and X number of web servers will do the job. The automation takes care of them. Then it's architecture. So a dev, as long as a dev writes code, there should be a person who has to actually sit with the dev team to actually architect the infrastructure. So he has to take decisions on how to scale the architecture and how to make the architecture reliable. That's why the sysadmin actually got the name Devops. The sysadmin paradigm changed to Devops, because a person who bridges the gap between the operations world and who bridges the gap with the dev world. Or else earlier how they worked is a dev team will independently develop code, and once their monolith is ready, it could be a jar file or it could be whatever it is, they actually put a ticket. The DevOps team, the sysadmin team understands, oh, this is the requirement, they build the infrastructure, and then the ticket is closed, the product is deployed, and the release cycles are like 6 months, 5 months. It's not a continuous release cycle that people are talking about now. So, architecture for scale. What is architecture for scale? So, architect for scale is, there are multiple ways to architect. One is a vertical scaling. That's what people initially thought. You scale your systems so high, like by as big instances as you could, that could serve your traffic. So examples, mainframe computers, supercomputers, where it's that man who's standing there, the sumo wrestler, is what your vertical scaling is. What a horizontal scaling is, you have many such kids who stand opposite to the sumo wrestler. You make many such small kids. At one scale, you can actually do the same job what the sumo wrestler does. One of the things what the first speaker said, Mohamed Imran said, is if your project actually needed 4 GB, the basic requirement of RAM, and if that kit, a small instance, is not even having 4 GB RAM, obviously it can't do. So your basic requirement should be even a smaller scale hardware that you start with should have their minimal requirement satisfied. Then once you find the right size, you can just horizontally scale it. Then you can actually scale your infra. But this has a caveat. Why a dev has to sit with the DevOps to achieve this? Because everybody knows how a user management is done, right? You need to maintain a session, and an equivalent session data is stored on the server side, and some data is stored on the client side. Now let's take that as an example. If data is stored on the local file system, the session is, user session is, and you are actually doing a scaling. So what does scale mean? I will put multiple web servers for user management, and there is a load balancer in the middle, and my request with my session data session cookie can go to any of these web servers. Then if the session identifier is on the server, do you think will it work? It's locally stored on the server. Then like there is a session ID, session cookie for me, XYZ, and there are 10 servers. Server 1 has on its local file system, XYZ means this user, this data. But my request can go to session user server 2 also, server 3 also, server 4 also. Then obviously server 3 can't find 2 AM. So on a horizontal scaling, such components come into picture where the DevOps say you need to use something like JWT, or you need to use a session store, probably a Redis or a database, so that your app has become stateless. There is nothing. Your app depends on the local file system, so the request can hit any of these servers, and there is no skewed ratio that the request has to hit. So that's a horizontal scaling part. Once you achieve horizontal scaling, then auto scaling comes into picture, because cost is a thing. You can actually downscale and upscale based on whatever metric you need. Then another thing is a tooling, selection of tools. So select maximum when if it's a Java app, you could run it on Tomcat, or you could run it on Jetty, whatever you want to run. Now there is a database you are going to access. Now you see the database access is actually taking more time. Then a DevOps is a person, or a dev could also do the task. He has to see how to reduce the latency. Probably you could put a cache in the middle. So you could put a Redis or a memcache which caches the data. So these architectural decisions, somebody in the company has to take it. If whoever is the person who's taking it, he is actually doing the DevOps tooling job. And auto scaling in DBs are not much possible in current scenario, because the data has to be also moved. The data has to be replicated. And most of the DBs which support scaling also says don't do it when you are on a high load, because the data replication is also going to cause you more load. Usually it runs at a lower priority, but it will cause more load. So these architectural decisions somebody in the company should know. Same thing with respect to putting a CDN in the frame, configuring the CDN, where your SSL traffic is going to get offloaded, how long CDN is going to cache it, and how to purge CDN cache. So all these architecture decisions has to be defined by somebody in the team. And availability. So one of the most common things that a web startup or any web-based companies can't have is downtime. So if it's a local brick and mortar shop, we can just take a day off when a renovation happens inside the shop. But that's not the luxury that web-based companies are having. All the web-based companies are supposed to have a high uptime, and gone are the days where when you see a maintenance page on sites. Even people are getting really innovative on the 500 pages. Like Google has a 500 page which says we detected an issue, we have sent a bunch of monkeys to debug for you. So people are actually ashamed. It becomes WhatsApp for you. So it depends on the scale also. Not everything applies for all companies. For a smaller company, yeah, it's called SLA. How long you can go down? Like you can go down, and you can go down for 2 minutes in an hour, for an hour in a day. So each of this converts to a number. So that SLA that the team has to maintain. So a DevOps or somebody who is taking care of this availability part has to make sure their company sticks to that SLA. So to calculate SLA, there are multiple ways to calculate SLA. We will see on the monitoring part how do we calculate SLA. So how this high availability component comes in? You have to find single point of failures in the infrastructure. Initially, on your first phase, there can be single point of failures, because making the product live is the most important thing than fixing single point of failures. But once you want to stay in the market, you can't have downtimes. So obviously, you have to fix the single point of failures. So to fix single point of failures, there are again multiple articles available. How do you go multiple regions, multiple availability zones in the public cloud? And for a database, of course, you have to have a backup and replicas. So there is a caveat again, backup and replicas are not the same. Replicas are a live replication of the state of the master to the slaves. So that replication also replicates if a person has deleted the table, that replicates the slaves as well. So if it is a wrong deletion, your data is gone in all replicas as well. There is also something that you have to do is in-time snapshots. So once in a while, once in a day or once in a week, like IRCTC, which says I go down for DB maintenance. Not all the companies have luxury, but you can go down. I mean, you can actually do a MySQL snapshot or a PostgreSQL if you use. Do a snapshot, put it on some other place, keep the data. So at least if somebody has done some mistake, you have the data till that hour. You have the data till that day. And if you do once in a week, you have at least data till the past week. You lost the newer data, so you have something instead of nothing. So backup is completely different from replicas. So this is all the availability funda that somebody in the team has to take care. Then maintain. So once the infrastructure is up, there has to be a way to determine that the infrastructure is running fine. Because now the infrastructure has become completely a code and the infrastructure has become complex, that it's abstracted. There should be some way you need to identify that the infrastructure is working fine. It's similar to a patient put on a ventilator and all his essentials are being monitored. So same thing, the CPU is monitored, disk space is monitored, a number of files in Apache is monitored, everything is monitored. This is how you actually figure out an SLA. So SLAs is something like number of 500s I serve and number of responses I serve after a latency of X milliseconds are considered to be out of my SLA. So treat them as failures and count the number of failures and try to bring your SLA as high as possible so that your failures are minimized. And so SLA is mostly driven by business, but Google has something called error budget where you have an SLA and you have error budget. So they have a demarcation, they have two demarcations. The first demarcation is error budget, so they can make their systems can go down in the error budget time, and there is a ballooning between error space and error budget and SLA. That is when they make a feature addition or when you upgrade an infrastructure, something wrong has happened, then your system can actually take that balloon to go down. If it goes down beyond that, then your system is not going for an upgrade for this quarter or for this month, whatever is your SLA is, because you have actually breached your SLA. So it's again, if it's a small team, it's again, there is some way of measurement that your team has to have to know that the system is working fine. So you have to, there are tools for this, collecting, telegraph. So all these tools collect necessary info from a system and they pass it on to whatever endpoint you say. InfluxDB is a data store for time series, Graphite is a data store for time series, you can put the data anywhere. And for monitoring, you have Nagios or Jabex, there are a bunch of tools to do it. And on-call automation, so you need to get a page when an issue happens. And if a team gets a lot of page, that means they get alert fatigue. That is, they are getting called too much in the night. So then again, they are probably deaths left in the system to make the product live. You need to go back, fix them. So this maintainability part becomes a feedback loop to your system. Then one another thing recently became part of the Devops is security. So the Devops team is some places called as DevSecOps. So it's up to people's innovation to keep names. So yeah. So but there are certain, I have seen in many companies certain small basic principles are not followed. So the infrastructure has become completely insecure. So you need to put data in public only. You need to put public endpoints only if they are absolutely required. If there are no public endpoints needed, then the endpoint should not be in public itself. So public, you should have, every cloud provider has this, You should have a separation as public and private zones. Private zones will have only private IPs. You need to log in via a VPN or you need to jump via a patient host. You should not jump directly. Not all your boxes should be reachable via public IP. One wrong security group where everything is allowed, the box becomes vulnerable immediately. So this is something that is the responsibility of a DevOps person to make sure the network is architectured such that only things that are necessary is listening on public IPs. And there's another thing that DevOps person has to do if it's an application that is running. The application should always run as a non-privileged user. If there is a vulnerability in application, even Elasticsearch, which is commonly used on their 0.9 version, had a remote code execution vulnerability. Every such remote code execution vulnerability is possible in most of the tools. So once you have a remote code execution vulnerability and somebody breaks it and comes into your system, he is the user as the application runs. If the application runs as root user, he is a root. If your application runs as non-root user, he is not root. So make your application run always as non-root user so that your application always runs underprivileged and does not, even if a person comes in, he can't do much harm to your system. And the third thing is, this is again, these two are compulsory, I think, at any scale. Beyond that, it's up to the scale of the company. You can actually restrict logins of people. You can technically restrict logins of the people to the extent that nobody has to log into a server. All the logs are connected and streamed at some other place. People see at that place there is nobody who is logging into the server, and there is immutability that no changes happen to the server. If a change has to happen in the container world right now, people actually spawn new containers, destroy the old containers, or you can spawn new database instances and destroy old database instances or Google instances or whatever you have. What is the operability review is there is somebody in the team before a product is going live has to actually see all the security principles and see if it is followed and has to give a sign off. So I would put this in a responsibility of DevOps, a person who actually does it, who actually sees the architecture of the product is actually secure, all the applications are following the basic principles laid down by the organization. And vulnerabilities, everyone now one day you see this term meltdown vulnerability which came on Intel, you see it's like little bad heartbeat vulnerability, little while back came, then there was a Moodle vulnerability on HTTPS. So once in a while all these vulnerabilities do come in. On a network manager a vulnerability had come. So all these vulnerabilities do come in. So these vulnerabilities has to be patched by somebody. The AMIs has to be updated. Your container images has to be updated. So this again falls this iterative patching, updating of softwares, and sitting with the dev team to modify their code base for the upgraded version of software. All this falls under a DevSecOps line. Optimization. So there can be cases where the software, whatever you use, the application you use, out of box will not satisfy your use case. Or else you could have satisfied your use case till you became X amounts popular. Once you became 2x popular, the application might not have been scaling to you. So there are scaling at multiple layers. The application can be scaled. There are a lot of parameters in each of these DBs for timeouts, for idle timeouts, for how many concurrent connections they can handle, for how much buffers they can use, all these things. And for Redis, again, it has its own how long the event loop can run, how frequent it has to write the data to process the data to disk. So each application has Apache, for example, has number of worker processes it has to run. Should it run as a worker process mode or thread mode? So somebody has to actually understand each of the application we use in the infrastructure, and he has to know that okay, I hit this issue, how do I scale? How do I optimize? Sometimes even the OS has to be optimized. The OS can put its own things. The OS exposes the CTL and U limits. These are all OS exposes as variables that you can tweak. So the OS gives modifies performance accordingly. And you can also, there are at some scale the existing tool obviously becomes, you breach the scale of the existing tool. It's very rare to happen only when you reach beyond a certain scale, which is actually a good thing because you are successful, you reached beyond the scale. In those cases, you can actually start building your own custom modules for Apache. Every common tools have Redis, Apache, Nginx allows you to write your own custom modules. But you should be really careful. If you write your own custom modules, it should be a reason that you have reached the existing scale that the system can handle. Or you are adding a feature that the system is supposed to handle. Or else you actually might reinvent the wheel. There might be a reason why people haven't written it as a custom module and you're trying to reinvent the wheel. Then troubleshooting. So the tracing is one way of troubleshooting. You have logs, you have metrics. So whenever a failure has happened, you go to your metric dashboard, see which graph has abnormally behaved during the time. You look at logs, how do logs do, and if you have figured out that this particular request is giving me an issue, then tracing is one way. You can go back to the trace logs and see. If you don't have tracing, there are tools like Neuralink, application APMs. They are called APMs. So application performance monitors. You can use them. They are mostly paid ones. Or you can, if you want to do it on your own, you can do it. You can replay the request, do a TCP down, see what is happening, who sent this, reset first, who actually broke the TCP connection, or strace, DDB. You can use anything to debug your applications. So all this is a resort, somebody does it on your team, and he finds an RCA, and there is actually a feedback going back to the system to fix it. If it's not code, not production, not dev code, this some guy takes responsibility in fixing it. Then again, deployment. Yeah. So once you push your code, it has to be deployed. There are a lot of ways to deploy. There are a lot of CI/CD tools available. Capistrano, Jenkins, Go. There are a bunch of tools available. Now, how do people do deployments? It has again changed. Earlier deployments used to be just a git pull, restart your services, or deployments used to be you do rsync of the file. Now what happens in deployments, there are literally people spawning new VMs or new containers with the newer code, and your old code still stays. People jump traffic to the new code. If the new code is not performing as it is expected to, people switch back to the old code. If new code performs as expected, the new release performs as expected, people just shut down the old cluster and go off, because no longer hardware is a limitation for people. So that is called blueprint deployment. There can be any number of pipelines now built over deployment. I think it in itself is a separate topic to talk on. So somebody who actually sits with the devs, helps them in building the pipeline, is a person who is part of the DevOps team. So yeah, there is another misconception. I was talking to one of my friends who is running a company. He said, I need a person to build the basic infrastructure and give it to me. Then I don't. Then my devs will start pushing code to it. After building the basic infrastructure and securing the platform, he doesn't think there is a role for a person who works on an infrastructure basis. On a side note, DevOps is a team which should also work iteratively, which should not scale up their infrastructure, or which should not build an infrastructure for some 3 years in advance today itself. There might be some product which could get scratched, there could be something which might not go as expected. So a DevOps team should also work iteratively. Not everything that I discussed on the slide has to be there on day zero, but the team should always think about automation, availability, scale, and stuff. And so every technology that we talk about, microservices or availability, everything is scaling, everything is at the end of the day, is a tech solution to a business problem, is to a managerial problem. So everything, if your business demands, what is the ROI, you are actually going to deliver it. So a DevOps team is going to iteratively deliver it when the business demands it. Instead of expecting a DevOps to give everything and on the first day itself, it's also a wrong assumption. So that's all I have about this is a brief intro, because I felt everybody should know what a DevOps team is. That's it. So this is my, I'm done pretty much. If you have any questions, you can let me know, or if you want to discuss about existing tools or how to push them. If you have some problems, you could catch me up.
When you started your career, you started as a developer and then you moved to DevOps?
No, I started my career as a DevOps.
Okay.
So yeah, I'm a campus recruit. I started as Devops. And I did from these jobs.
Do we have any more questions? Thank you, Kalyan. So before we close, we have our puzzle winners. Do we have Mayank, Ramesh, and Piyush here? Mayank Verma, Ramesh Kumar, and Piyush Agarwal. Okay. So a round of applause, please, for our winners. Thank you. So thank you all for coming today on a Saturday and spending your time with us. Thank you for being a very interactive audience. A special thank you to all of our speakers, Vivek and Kalyan. So Imran had to leave, keeping in mind that he stays very much far away. So thank you to our partners as well, Hasgeek as well as 91 Springboard MG Road. And if any of you all are looking for a payment gateway, you can always reach out to us. We are here. And thank you all once again. We are opening the session to networking. There are roles and soft links on the back there. Thank you so much.